Okay, the next part we're going to look at on the starter is the armature itself here, which is the motor here. We can see on this is our link pivot pin that goes from our starter solenoid, and as it pushes, it rotates and pushes the pinion gear to engage with the flywheel up there. And you can see it as it's moving, it's actually twisting there. So as it does turn into the flywheel ring gear teeth. The other feature they have on these, because these are what's known as a straight cut or spur gear, is that each of the teeth there, if you can see around the edges here, are chamfered off to make engagement with the actual ring gear go a little bit easier. The sprag clutch then on the end, we said, was a one-way clutch, or sometimes called the overrun clutch, so it allowed the pinion turn in one way but not the other. It won't allow it to turn the shaft in the other way, so that turns the whole motor, whereas when it turns that way, it's not turning it, so it turns that way. It can turn freely. When it turns this way, it'll turn the whole motor. Okay, we can also see why or how it does this. You'll see it rotating up and out, twisting that pinion gear, and how it does that is in behind here on these worm gear on the shaft in here. So as it turns forward, it actually rotates that pinion gear in a direction. Okay, now really what we're looking at here is, as we've seen before on some of the animations, is the armature winding. Now each one of these windings, we said, is insulated from the other, so, and the segments here are what they call the commutator segments, right? So this segment here is linked to the winding that it's attached to, and only that winding. So when the brush pushes a current through it, say that segment there, goes down the winding and back out, back to where it came from, right, out the other side of the winding. So I end up having a current heading in two directions at the one time, down the same winding. One of them current's heading that way. The same current as it's coming back is heading the opposite direction, therefore giving me a north and south magnetic field, two different polarities of the magnetic field on the one winding, which starts me spinning because it's going to fight with the magnetic field that exists between the permanent magnets or the wired magnets that are there, either series wound or parallel wound electromagnets that we have in the starter. But we're just going to concentrate on the motor here for a second and take a look. So again, when we're testing this, it's going to be just simple resistance testing or even continuity testing, because what we want to happen is that each one of these segments is connected to the next segment. So if we pick one segment on it, touch them off one of them. Let's just turn it on to tone so we have a better idea what's connected and what's not. That was probably easier to do on this armature here. Easier to see on the camera on this armature here. Or actually, we might use this one like this. Yeah. Okay. So, as we look at it there, all of those commutator segments should be connected to one another. So there's a couple of different ways of doing this. Some people do the 12 and 6 o'clock test. Just keep moving around the actual segments on it. I find the easiest one to use is just pick a segment. So again, checking our meter that it's working. Touch. Listen for our tone. So pick a segment and just move all the way around it. And we just continue to go all the way around, making sure we're getting a tone on each one of these segments as we go. Okay, so all of those all the way around should be connected, so we should get continuity all the way around on the commutator. Now, in the same position or wherever you want on the commutator, pick one of the segments, and what we shouldn't have is any connection with the actual armature shaft itself here. So we should be open circuit here, which means no tone, and the same again on the body of the motor here, open circuit here. So it's a quick and easy test to do on this. Once they're all connected together, commutator looks good, and once the commutator does not short with the shaft or the external body here on the armature itself, the armature is in good condition. Now, there was a couple of other things we said on the armature here. In between these segments here, we should have a break in between them. Now, what tends to happen is as the brushes wear, the carbon impregnated copper gets pushed down into these segments on these and can cause a short circuit. So what used to happen, and you can see it better on this one here, is we used to scrape these out just with the back end of a blade or the back end of a paper clip, just to pull out all the carbon impregnated stuff to stop it short circuiting across it. Now, you didn't want to cut in too far because they're quite a thin layer of copper here. So what we didn't want to do is cut into that insulator here on the top end and make that brittle. But again, easy enough to take a look at them. Now, giveaway stuff that there's something going wrong here is if we look at the commutator and we can see a blue tinge off around here on the commutator, which is indicating that the brush is not sitting right up against it and it's causing an arc to happen. If that happens, you may see cracking of the commutator segments, but they will definitely have a blue tinge to it where they've been overheating. The brushes themselves then, in our main body of our alternator, this is called our yoke, starter yoke here now. So the brush kit is normally here on the back of it. Remember, this is our link coming from our motor, so that is going to become a positive when our starter solenoid loops across and bridges out the two major poles, the B plus and the M on the solenoid. So this will become a positive link in. Now if we look at it here, as it comes in, it parallels out. Sorry, it goes around here, so there's one brush it goes to there, and we'll see. So if we're testing that, we want to go to the end of the brush, see what we've got. And it's normal for these, if we're looking at them, to have nearly all the time we will have the brushes across from one another. So this will be a positive brush here, this will probably be a positive brush here, and then these will be earth brushes on this side. So when I'm linked to the positive, I should have no continuity between either of them and the positive wire I'm on here. But then when I go to earth with them, stretch the body anywhere, and we should link in. If we get a good clean connection in here, we'll have to go from the bottom here, I'd say. Nice clean connection there. So good tone on that one, and more than likely the one directly across from it is okay. Right, so again, these brushes are just connected on from this point here up to the end here, and they will have a certain length when they're new. So again, we'll check them here and here. Good brush. Good brush. Good brush. And then from the end of this onto it. Good brush. But, so the connection is good along the brushes, but what I can see is where the wire goes into that brush is getting quite close to the end where the contact is made. So that brush is nearly wore out. We can see even by it here, there's normally springs in behind here where the brush sits to keep them pressed out against the commutator. And if they sat out about there, look at the amount of space behind them, which indicates that there's probably a fair bit of wear on them at this stage in the game. So you may want to think about replacing those and keeping your commutator in good condition by keeping the brushes in good condition. So again, they're just basic operation here. Now this particular starter motor inside the yoke has wound electromagnets that we're going to cause inside here. You can see it in there, as opposed to permanent magnets in it. And this is a way of creating two magnetic fields. So I can create a magnetic field across this and a magnetic field inside the armature when it goes into it and spin it. So therefore one magnetic field will be fighting against the other in there and causing the armature to spin around. It's just a different way of doing it. As we said, the downside to the permanent magnet motors was the two issues that magnets have. They don't like heat or too much heat, and we're going to have an awful lot of current passing through here, and it's bolted up against a hot engine for the vast majority of its life. And the other thing was shock then, so we were all taught to do this when we heard that click from the starter motor, give it a tap as somebody was turning the key on it to try and kick start these in case the brushes were just stuck against the commutator. But in actual fact, on the permanent magnet ones, shock like that will decrease the magnetism and will cause the actual motor to get weaker. So we can sometimes cause it to happen unknowing, but there's always a reason why a starter motor won't turn. Sometimes you just have to take it apart to figure out what it is or what's going on inside it. So by doing the simple tests on the actual solenoid, the motor and stator connections on it, and having a look around at them, and then having a check of the brush contacts here and making sure they're all in good condition, we can normally get most starters up and running again, bar there is an actual open circuit inside the armature winding here on one or two of them, which will make it a weak motor anyhow. We also want to inspect the pinion teeth, make sure they're not gouged out of it, and when we have the starter motor out, we need to take a look at the ring gear on the flywheel as well and make sure that's okay. Now this little ring here stops because when the solenoid engages the pinion like that, that stops it. And the reason why it stops it there is we do not want that ring gear going over the other side of the ring gear teeth, the pinion teeth going over the ring gear teeth and getting caught in behind it and jammed at that stage, right? So this limits the travel on it here. We still have a nose in here that's going to sit inside a bearing, front cone bearing up the front up here, if we look in there on it. If we can see down in there, can we? Yeah, it's a bit of a nose bearing down there to help the actual just in there, the starter motor shaft, the armature shaft sit easy on it, and on this particular one here we just have a plastic link, so remember that would be face down like that, pinion pushed back, and then the solenoid would push it forward and engage the ring gear into the or the pinion gear into the ring gear teeth. So again, simple test with it. They're not that complicated and haven't been for years. There are some that have gear reduction on it, and we saw a few of them in the CDX. That's one there. I don't know whether you can see in the back of it there, but this actual plate in here has the sun gears in it. You may be able to see into it there. Let me have a look. Yeah, you can just see it inside there. So you can see it turning. I'm turning the pinion on the outside, and that's turning the planet and sun gears, and they're actually spinning around in a circle there. Again, all of that stuff is just about taking a fast moving or fast rotating starter motor and slowing its speed down and making the speed turn into a torque for me, to give me a torque, because remember, the starter motor has to be a high torque motor to actually get that engine to spin over from dead stop. I think that's about it on the starter motor stuff. So if you have a look through the notes, have a look at these videos, any questions about them, give me a ring or an email, and we'll try and sort out, iron out any queries you have. Okay, thanks for that. Bye.